Okay, we talked about the GR equation motion being geodesic equation. Now we're going to talk about more fully how to find the whole GR apparatus equations. So how to go from Newton to Einstein. uh, Remember, Newtonian potential uh, in Einstein becomes the metric tensor, 10 component metric tensor, and the equation motion becomes geodesic equation, which the Kursov symbol depends on the first order of the metric. Okay. Now the field equation, you have the Newtonian field equation, the Laplace acting on the gravitational potential is proportional to Newton's constant times the mass density. The question, what would be the GR extension? What GR extension would be, which, for example, in the Newtonian limit reduced to Newton's equation? So we're looking for the field equation for uh, GR, which is actually Einstein's equation. Now, the right-hand side, so we see how to go from here to here. So right-hand side of Newton's equation is, we suggest, should be proportional to the symmetric energy momentum tensor, because the mass density is simply the zero component of the energy momentum tensor. So it suggests the tensor equation for GR field equation should be a tensor of rank 2. In fact, it's symmetric because T mu nu is symmetric. And because we want the field equation to be covariant, has to be a tensor equation. The right-hand side should be symmetric because the tensor is symmetric. And the left-hand side must have the same tensor structure. Okay, so therefore the right-hand side is the energy momentum tensor. The right-hand side is also the same tensor structure, and the kappa is proportional constant. We expect it to be proportional to Newton's constant. So, the left-hand side of this equation, we expect some operator acting on potential. The reason because the Newton equation has some differential operator acting on the gravitational potential. So we expect this some operator acting on the metric tensor. We expect both the secondary respect to the metric tensor as well as the nonlinear first derivative squared. So this is all g, this is g squared, so it's nonlinear. So energy, just like mass, is source of gravity, and the gravitational field themselves holds energy, right? Um, so therefore, we expect the gravitational field itself is a source of gravity. Remember, electromagnetic energy density is quadratic in the field E squared plus B squared. So we expect gravitational field energy density to be first derivative gravitational potential has the first derivative of the metric tensor squared. So in other words, we expect the left-hand side to be a symmetric rank 2 tensor, and it's a nonlinear second derivative of the metric composed not only the second derivative but also the first derivative squared. Now the second derivative, because the Kursov symbol is first derivative, so second derivative can be gotten from first derivative of the Kursov symbol, and or for the first derivative g squared can be gotten from square of the Kursov symbol. So some linear combination of first derivative Kursov symbol plus square of Kursov symbol. And in fact, you see this is precisely the curvature. We expect the second derivative measures to be curvature, but in particular, this kind of factor will come in. You see, we didn't expect that the equation be covariant under general transformations to be tensor equations. That's enough to restrict to this, we know, and some expect what kind of feature it must have. So this is the power of the symmetry principle. Anyway, so the left hand side of the field equation is something to do with curvature. So let's talk about curvature. Curvature tells me is a coordinate independent criterion to decide whether space is curved or not. Okay. The, we said only a flat space can have a constant metric tensor, but a position or constant metric tensor does that imply a curved space? Because in a flat space you can have curvilinear, for example, polar coordinates. You still can have a position dependent metric. Okay. So so therefore, metric by itself is not good criterion to decide whether space is curved or not. And what a great contribution Gauss that he found that you can find a certain quantity we now call Gaussian curvature. This second derivative of the metric, which is coordinate, can decide whether the space is curved or not in a coordinate independent way. It was uh, if it's zero, it's a flat space. If it's not zero, it's curved. Now here I'm write down for the two-dimensional surface Gaussian curvature. We choose to write down for a diagonal metric. It was off diagonal to zero, but that's not a particular restriction because whenever you have a orthogonal coordinates, you have a diagonal metric. Okay, so it's somewhat complicated looking expression. I'm not going to derive it later on. If we want to know the general curvature, in principle, you can derive it from this. Now, for a flat plane, let's say it has a Cartesian coordinates, so therefore the metric is constant. And clearly, in this case, if constant, all the derivative vanishes, right? So because the first derivative, second derivative all vanish, and so therefore k equals zero. So therefore, k equals zero corresponds to a flat plane. And I would say this is a coordinate independent statement. Suppose I, instead of using Cartesian coordinates, I use polar coordinates for a flat plane. And now I have a position dependent metric, okay? And but the G11 is 1 and G22 is R squared. R is the X1, so X1 squared. And so uh, uh, the differential G22 with respect to X1, I get 2X1. And the second derivative of the G22, different one more time, I get factor 2. Okay. Now let's see. For this coordinates, well, in principle, we should also get 0 for the because then it shows it's coordinate independent. I can using the Gaussian curvature to decide whether space is curved or not. First of all, G11 is a constant, so all the derivative term involved G11 is 0. So only really two terms left, okay, which and the second derivative is 2, so this term is 2, and this term 2x1 squared. Okay, so therefore k g11 is 1, so just 2 g22 which is x1 squared, and this one is minus 2, and this one here is 2 x1 squared, and here the first derivative is squared. So uh, this factor cancels. Here's factor squared 4. So therefore I get factor 2 here. 2 just cancels the minus 2 here, so equal to 0. So I can show that the curvature indeed is 0 in the polar coordinate system. So therefore I can use k in a coordinate independent manner to decide whether space is flat or not. I'm going to leave you as a break exercise to check some other cases.